the first topic. We're starting with this first topic, which is forces and equilibrium. And we're expected to identify the forces acting in a given situation, understand the vector nature of force, and find and use components and resultants. And then we use the principle that when a particle is in equilibrium, the vector sum of the forces acting is zero, or equivalently that the sum of the components in any direction is zero. All of this I will explain as we continue. Then we need to understand that a contact force between two surfaces can be represented by two components, the normal component and the frictional component. I'll talk about that. And then we use the model of a smooth contact and understand the limitations of this model. And we understand the concept of limiting friction or limiting equilibrium, and use coefficient of friction, which is F equal to mu r, or F less than or equal to mu r as appropriate. Then we also need to draw what we call force diagrams or vector diagram. We will not be required to get those values by scale drawing, which if you remember you did at O-level physics. Vector, and we solve by resolving forces in a given direction. There are some other principles that you may want to know, what we call Lami's theorem and all of that, but they are not compulsory. You can always use different methods to solve that. All right, so let's meet on the next page. I want to start talking about each of these. I'm on the next page, page 2 of 2. All right, we know that the vector is a quantity that has direction and magnitude. Magnitude and direction. In other words, it has a size and it has a direction. Can you give me an example of a vector quantity? Pardon? Velocity, okay. Compared to speed. Speed is scalar because speed is not interested in direction, it's just size. But velocity is a vector quantity because it has to do with the size, which is magnitude, and the direction. So you have other quantities like acceleration, you have displacement. Are we listening? Please, I need us to pay full attention. Acceleration, displacement, and momentum, But when you come to scalar, you have quantities like energy, distance, speed, time, temperature, and what have you, mass. They are all scalar quantities because nobody's interested in direction. If I say the mass of a piece of material is 20 kilograms, you wouldn't be thinking of direction. It's just the size, the magnitude that's important. But if I say a force of 20 Newton, you want to know which direction is that force. Because a force of 20 Newton acting towards you is different from a force of 20 Newton acting towards me. So both size, 20 Newton, and direction towards you or towards me are important in describing vectors. I think we're good with that? All right. Okay. You can recall your trigonometry ratio whenever you have a right angle triangle. For instance, if I have a force like this force can be resolved into two components, what we call the horizontal component and the vertical component. Okay, let me use a different color of marker for the horizontal component. What I would rather do is use a red marker for the main force. This is the force acting this way at a given angle, which I will call theta. And this force can be resolved. I will explain to you what I mean by resolved. Can be resolved into two components. The horizontal component I represented with blue, and the vertical component I represented with yellow. Now, resolving a force is basically splitting it into two, as it were. Give some part to the horizontal and give some part to the vertical. In fact, we'll be doing a lot of this. You know, you split a force into two, give some part to a particular plane, which can be a horizontal plane, and give the other part to a particular plane, which could be a vertical plane. Usually, when we are resolving forces into components, we give a part parallel to a plane of reference, and then another part perpendicular to a plane of reference. What do I really mean? The plane of reference could be a horizontal line like this. It can be a horizontal line like this. And then this force represented in red, is acting along this horizontal line. Let me represent the horizontal line actually touching, as close as possible, touching the point of action of the force. You know. So a force is acting from this position. I can call this position P. And the value of the force, I will represent it with R. Acting from that position P. You know, the axis of reference, what we are going to use as our basis of reference, is this horizontal line I represented with a black marker. Now, this force represented in red, we can split it into two. Now, when I say split it into two, I don't necessarily mean that we split it into two equal parts. We split it into two and give a part of it to that horizontal plane and the other remaining part to a plane that is at 90 degrees to it. So that's what I mean by a part to a plane parallel to, okay, so I will write it. Resolving forces is done by splitting, and I'm going to put it in quotation mark. Splitting has double T, am I right? Splitting is what I'm writing, showing on your screen. Okay, splitting the force into two components. The two components are A, parallel to a given plane of reference. So let me just correct it. One of the components will be the one parallel to a given plane of reference. My writing should be neater than this. A given plane of reference. It means I'm not sitting properly. My sitting position is not comfortable. I'm not feeling comfortable. All right. Parallel to a given plane of reference, and then the other one, I, the first one is I, parallel to a given plane of reference, then I, perpendicular to that same given plane of reference. What does the word perpendicular mean? Yeah, given at 90 degrees, perpendicular to a given plane of reference. So this is the force R, represented in red. We're going to split the force into two. One will be parallel to a given plane of reference, which is the black line. And of course, the one that will be parallel to it will be the blue one, the one I showed with the blue arrow. Then another component will be perpendicular to it, which is the yellow one. You know, so to do that, you just use a simple knowledge of trigonometric ratios. If we call this horizontal component x and the vertical component y, what's the value of x with respect to r and y? R and theta. What's the value of x with respect to r and theta? Do you have an idea? Do you remember your SOHCAHTOA? SOHCAHTOA. We use this extensively. Trigonometry ratio. Pardon? Yeah, you are right.
X over R.
Excellent. Cos is adjacent over hypotenuse, isn't it? Which side is adjacent with reference to the angle theta? X is adjacent. Which side is opposite? Y is opposite. And R is what? Hypotenuse. So if we are looking for X, we are going to use adjacent and hypotenuse, which is the R given. Usually the R could be given. Let me just call it so that we actually start practicing. Let's call this R 10 Newton and call this theta 30 degrees so that we start working immediately. Theta is 30 degrees. So let's find X. For X, use cosine. X will be, for X we can do X over R is equal to cos theta. So X is equal to R cos theta. Also for Y, what can we do for Y? Let's concentrate. Y is what?
Sine theta.
Okay, because Y over R is equal to sine theta, isn't it? So Y is equal to R sine theta. You don't have to go through all these rigorous steps. The simple idea is the side that is adjacent to the angle that is under consideration will be R cos theta. That is the resultant force you are splitting cos that angle. Now the side that is opposite to the angle under consideration will simply be R sin theta. All right, let's take a simple example. You can find me on the next page. Before I do this, I want to tell us that whenever forces are acting, several forces are acting on an object or from an object. The forces that are along a defined plane of reference or perpendicular to it will not require resolution. Let me explain. I will explain with this diagram before we look at it. So look at a number of forces. This is an object. I'm on page 3 of 3. This is an object, and I have forces acting. I will represent it with different color. This is one force acting, the yellow one. And then another force, the black one, is acting this way. And I have another one acting this way. Maybe I can include a blue one acting this way. Now, in this particular diagram, our standard plane of reference is horizontal. So forces that are parallel to the horizontal plane do not require resolution. In other words, they are already defined in their right position. Because resolution is basically to split a force, give some part to the horizontal axis and give another part to the vertical axis. So if a force is already parallel to the horizontal axis, we don't need to split it again. We just drop it there. So for instance, which force is parallel to the horizontal axis in the diagram I showed? Which color? Parallel to the horizontal axis. It's showing a different color on your parallel. Oh, maybe it's showing a different color at your end. at my end, what I have is blue. Is blue that is I'm on page 3 of 3.
I thought blue. I think you said we should find what's parallel to blue.
Oh, sorry. I meant which force is parallel to the horizontal axis. Blue is the one that is lying on the horizontal axis, so to speak. Alright, so blue does not require resolution. In other words, it's already in its right plane. Also, forces that are perpendicular to that plane of reference will not require resolution. This is an exciting introduction. You will love it because I'm moving it further. Two forces that will not require resolution are the ones that are parallel to the plane of reference and the ones that are perpendicular to it. So blue is already parallel to this plane of reference, which is the horizontal. Which force is perpendicular to it? The black is perpendicular to it, so it will not require resolution. Meaning we don't need to split it. All other forces that are neither parallel to the plane of reference nor perpendicular to it will be split or resolved. So yellow will be resolved, green will be resolved, split, and then we give some part to horizontal and give some part to vertical. Alright, so in doing that, I might have to identify the angle that each one of them make with the axis. So let me use this as the axis of reference, which I will put in dotted lines so that it doesn't look like a force. Have you seen the red line I just drew?
Yes.
Okay, so you can even extend it to the other side. Extend it to the other side. I drew it in dotted lines. Okay, now if this yellow force makes angle 30 degrees to this horizontal and the value of the yellow force is 80 Newton, and then the black one makes, what angle does the black one make with the horizontal axis? 90. And of course it's perpendicular, so it doesn't require it. Even if you try to resolve it, you get the same answer, so there won't be any need. I will show you 50 Newton. Now the green one, let's give it 60 Newton or even 30 Newton so that it doesn't get so. And if it makes an angle of 20 degrees to the horizontal, it is always it's always recommended that you measure two the same plane of reference, which is in this case horizontal. I will measure all angles to the horizontal, all forces to the horizontal axis, even if their values were given to the vertical. Okay, this is what I mean. If I didn't give this one as 20 degrees, if I had given it as 70 degrees here, this 70 degrees is to the vertical axis, isn't it? I need to still get its value to the horizontal axis. So what is its value, the angle to its horizontal axis? 20. So it's the same thing. You can still work with that 70 and get the same answer, but for uniformity, it's always good to get all angles measured to the same plane of reference, so 20 degrees. All right, the blue one, I will give it 60 Newton. So I have 4 forces here: yellow 80, black 50, green 30, and blue 60, all acting from this point I dotted here. 2 of the forces will not require resolution: the blue and the black. The blue will not require resolution because it's already parallel to the plane of reference, horizontal. The black will not require resolution because it's already perpendicular at 90 degrees to the plane of reference. So we need to resolve the 80 degrees, 80 Newton and the 30 Newton. So this is what we do. Split it into 2. Give some part to horizontal and give some part to vertical, something like this. I can use a different color marker. Maybe I can use black, this, and this. And I want to explain something. Probably a different color marker will help us here. Let me be sure if what I've done has shown at your end. Okay, the black one is a part of it that is perpendicular to the plane of reference. The green one is a part of it that is horizontal. Now, I want to, you can show them with dotted lines, but they must be shown with arrows. How do we determine the direction they go? Now, this is what you need to know. If a force is going this way, the components must run in such a way that they will meet it. This is what I mean. This triangle I drew at the bottom, has it shown at the end? Has it shown at the end? Okay, the components must run in such a way that they will meet that force. They will meet the tip of that force. So the components, please let me redraw this and use straight edges. Component, one component, the other component. These components, I said, must run in such a way that they will meet the arrowhead of the main force we are splitting. Okay, so I will draw another one so that you draw the arrow, how the components will run. What I'm saying is actually very vital in the understanding of this. I've drawn another one, have you seen it? So I will draw the components. The components will also run in such a way that they will meet the main force we are splitting at its tip. So the arrows must come this way and this way. Did you get that? Perhaps one more to reinforce this understanding. If I have this, can I have one of you draw? By the way, if you want to draw, just hold down your shift button and draw. You'll be able to get a straight line. This is for you. The yellow one is for you, Daniel. And the green one is for you, Victoria. So draw the components. Hold down the shift button. Pick up a pen. Yellow one is for you. So this is Daniel, D. Boyo is B. And Victoria is V. Can you please use a different color of marker from the main drawing, Boyo? You can use the same color for both components, but the components should have a different color from the main. Hold down the shift button if you want to draw Vivango. This is resultant force for Victoria. Victoria, can you look at what you did? The arrows should be drawn, follow the same direction so that they will meet the tip of the resultant force. You can just undo if you are. That's better, Daniel. You can still use the shift stuff to draw. So I can mark, this is correct, 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 this is correct. Okay, we have it. What I will just do is to carry this question to the other side so that we solve it. I don't want to draw it again. So let's move it to the next page. I'm on the next page. I want us to now practice with this question. So the question is, find the resultant force. This is like a past question already. Find the resultant force. I'm on page 404. Have you found me there? Find the resultant force. By the way, the resultant force is the effective force of a system of forces. It's like one force that you can use to represent all the forces acting. In its simplest definition, if you have, like when people are in a tug of war, where if a group exerts a force of 50 Newton to the right, another group exerts a force of 30 Newton to the left, what's the resultant force? Pardon? 50 to the right, 30 to the left. 20 to the right. It's even good that you mention the direction, because force is a vector quantity, so direction is important. You know, when the forces are acting in opposite directions, you subtract, isn't it? But if they're acting in the same direction, you add. Okay. The beauty of magnets is helping you with your physics, because we're also going to do that in physics. You know. Okay. Well, that's the simplest form of resultant force. It's just a system of forces, the effective force of a system of forces. The thing about resultant force is, if we apply that same force in the opposite direction, we balance the other forces. I'm jumping the gun. Let me finish this. I'll remember what I just said. You will understand that. So let's find the resultant force of all these forces. Are we ready? Okay. So to find the resultant force, some forces will not require resolution. What are the forces again? We mentioned that some will not require resolution. What are they? 60 Newton will not require resolution because it's already on the horizontal plane. 50 Newton will not, because it's perpendicular to it. We need to resolve 80 and 30. So I've already drawn the components for 80 and 30. What's the value of the black one? Based on, without having to go through trigonometry ratio, can you just recall what we said on page 2 of 4? You can come back to page 2 of 4. For the one that is opposite, the opposite, you use r sine theta. For the one that is adjacent, you use r cos theta. Alright, so the black one will be what? This black line. R sine theta. In other words, 80 sine 30. Is that what you mean? Because the r is 80. Are we there? I'm on page 4 of 5. Page 4 of 5. Somebody will be helping us with the answer. So this is r. The r is, in this case, is 80 Newton, isn't it? The theta is 30. So this is 80 sine 30. So help us get the answer. 80 sine 30. Yeah, sine 30 is half. So 80 sine 30 should be 40. 40 Newton, right? Let's get the horizontal component. What's it? What's the value? 80 cos 30, is it not? 80 cos 30. Are we all following?
Yeah.
What's the value? 69.28. So 69.3. By the way, unless otherwise indicated, your answer should be rounded to 3 significant figures. But this is not the final answer. It's actually advisable to leave it to 1 significant figure or higher. So I might just allow it to 4 significant figures. You said it's 69.28, right? 28 Newton. Okay. Which other one requires resolution? The 30 Newton force, right? Let me just draw the components. For the 30 Newton force, I have this. You know, it has to go like this, and the other one, which has to go this way, isn't it? Yeah. What's the value of the yellow one? 20 sine 30. This is 20 sine 30. No, 30 sine 20, you're right. 30 sine 20. Thank you for the correction. 30 sine 20. 10.26 Newton. Why the black one is what?
Yeah,
30 cos 60.
No.
Cos 20.
Yes.
What did you get? 28.19. 28.19 Newton.
Yeah.
Alright, so we have all resolved. I think what we just do is to write out all the forces the ones going up and the ones going down. So let's have all the forces going up. And the ones going to the left and the ones going to the right. We have 40 going up. Do we have any other one going up? Vertically up?
No.
Let's see the ones that are going down. We have 50 going down. That the 50 that didn't require resolution. We also have 28.19 Newton. For the left, we have 69 point this, 69.28 Newton, and then we have the other one going this way. What's the value again?
60.
We have 60, and we have another one, right? There are two now. The one we resolved. 28.19. Have you forgotten? Oh, what is the value of? Oh, you gave me the wrong value for the one down. The one down is actually 10.626. Are we all here, everybody? Please make sure we are all concentrating. 10.26. Please, we need to make sure we are all concentrating. 10.26 is the one going down. And secondly, please, can you share with someone, just so that you don't lose out in our 10.26, right? So I have to change this one I wrote as, this is actually 10.26 Newton. This one is 28.19 Newton. So we have all this. Are we good on this? So let's begin to sum up. All the ones going down and all the ones going up. Let's resolve vertically. What will be the effective force vertically? 50 plus 10.26 minus 40, isn't it? What will be the value? 20.26. Actually, it is 50 plus 10.26 together, because minus 40. And you say you got 20.26. Please let me just write it down. 26 minus 40, you got 20.26. You said? The ones going, which one is bigger? The one going to the left, right? So let me show it. You know why I represented this one down? Because the one going down is bigger. So it will carry the day. So the other one will be 60 plus that minus that. 60 plus 28.19 minus what? 69.28. This gives 18.91, right? Newton. So we have two forces to work with now. 20.26 down and 18.91 to the left. I'm on the next page to represent it. 20.26 Newton down and what to the left? 18.91. 18.91 Newton to the left. How do we now find the resultant of these two forces? You can just use the hypotenuse, you know. So the hypotenuse is the resultant, which is this. Pythagoras theorem, right? So ours will be equal to square root of all that. You know what I'm doing? 20.29. 20.26 squared plus 18.91 squared. Are we in agreement? So what does that give us? What's R? So R is 27.71. 27.71, so we can now leave it in three single figures. So now, what is the direction, what we call direction? The direction is the angle which that resultant force makes with the plane of reference. So this theta. So how do we find theta? Theta will just be tan inverse of this. Am I speaking over your head? You know what I'm doing now? To find theta, it will be tan inverse of what over what? 20.26 over 18.91. Do you agree with me? Are you sure? Have you eventually joined? Oh, that's cool. Oh, okay. What's the tan inverse of that? Okay, that's 46.8. You round angles to one decimal place. Now, that is what we call direction. Okay? Direction is the theta. I want to tell you what I wanted to say, but I had to pause. The implication of this is this. Now, listen very attentively. You see, all these forces, there were 4 of them. One given force can be used to represent all of them, which is what? 27.7 Newton. That's the resultant. That's the effective force of all those system of forces acting at this angle, 46.8. The implication is, if I apply this particular force, 27.7 Newton, at this angle in the opposite direction, it will balance all those 4 forces. Because the resultant force is like the balance, the effective force, the net force of a system of forces. So if I apply 27.7 Newton, are you listening to me? At an angle of 46.8 to the horizontal, in the opposite direction, it will balance all those 4 forces. All those 4 forces are these forces. The 80 Newton yellow, the 50 Newton black, the 30 Newton green, and the 60 Newton blue on page 4 or 5. All I need to balance all of them is to apply a force of, go to the page 5 or 5 again, 27.7 Newton, acting at an angle of what? 46.8 to the horizontal in the opposite direction. Is that understood? Okay, so that's the thing about resultant force. All of these things we are doing is not just for the fun of it. In design, you take all of these things into consideration, particularly those of you that are going into engineering, structural engineering. You want to design a house, design any structure. You need to understand how forces are acting from different angles, the beams, the pillars, the columns, and all the weights, the dead weights, and what have you. And a particular force that can balance all. And that force should be sufficient enough to balance all, and balance it in such a way that it will be in equilibrium. Otherwise, the building will be tilting or even crumble, and all of that. Those things are taken into consideration by structural engineers when they are designing a structure, be it bridges, house, buildings, and what have you. Okay? This is principles of equilibrium. You will require that to solve most of those questions that I plan to give you. Principles of equilibrium. Now, for an object to be in equilibrium, you know, there are many ways to put it. You can say the vector sum of the forces in any given direction is 0, which simply means total forces in one direction is equal to total forces in the opposite direction. Did you get what I said? If an object is in equilibrium, total forces acting upwards, 20 Newton, must be equal to total forces acting downward, 20 Newton downwards. In other words, the resultant force will be what? 0. If the resultant force is 0, the object is in equilibrium. So forces in one direction upwards must be equal to forces in the opposite direction downwards. Forces in one direction to the right must be equal to total forces in the opposite direction to the left. So you need to apply that, you know. For instance, I think I can just pick a simple question to illustrate that. Let me see this one. Okay, let's see this one I want to solve. Page 14 of 20. Page 14 of 20. It says, given that tan alpha is 12 over 5 and tan theta is 4 over 3, show that the coplanar forces shown in the diagram are in equilibrium. In equilibrium, isn't it? Which means that total forces downwards must be equal to total forces upwards. Total forces to the right must be equal to total forces to the left. Or you can even say sum of the vector sum of the forces in any direction is equal to 0. Which means if I wanted to do that, I don't think it is anything a big deal. If you want to apply that, this is actually what I'm trying to say. If I wanted to use the vector sum equal to 0 for any particular direction, assuming this one is F1, this one is F2, this one is F3, this one is F4. Are you listening? Now, for it to be in equilibrium, F1 plus F2 vectorially must be equal to 0. That's what I'm saying. Also, F3 plus F4 vectorially must be equal to 0. F1 and F2 are the ones acting in the same plane. One to the right, the other one to the left. So whenever you are doing this, please take note. Yes, I like that.
F1 and F2 are equals to 0 when added together.
And we'll be equal to 0. I like that. You are really thinking, because if you're not thinking, you wouldn't observe this. In fact, in vector, when you represent one direction with a particular sign, the other direction should be an opposite sign. So if I want to represent F to the right as positive, like F2 positive, F1 has to be negative. So the addition will eventually give you 0. So you can express it like that, or you simply say F1 equal to F2. Is it not? Did you get that? So F1 must be equal to F2 in magnitude. F1 must be equal to F2. But you know that one is in one direction, the other one is in the opposite direction. So eventually one will carry a negative, the other one will carry a positive. Right? Okay. So that is for the horizontal forces. Horizontal forces F1 and F2. For the vertical forces F3 and F4, F3 must be equal to F4. Or F3 plus F4 equal to 0 vectorially. When we say vectorially, you also put the direction into consideration. So signs are important. Are we good with that? Okay, let's apply that here very quickly. Given that tan alpha is 12 over 5 and tan theta is 4 over 3, show that the coplanar forces shown in the diagram are in equilibrium. How do we apply that? What do you think we should do?
Show that the opposite forces
Must balance. First of all, there are forces that are not on the plane of reference. Neither are parallel to the plane of reference nor perpendicular to it, so we need to resolve them, right? What are the forces we need to resolve?
50
We need to resolve 50 Newton force and also resolve 78 Newton force. Do we all agree? Do we need to resolve 112 Newton? Why? It's already perpendicular to the plane of reference. So let's resolve. I think I need to zoom this thing in. Okay, you're seeing it very well. But at your end, you can zoom in as much as possible to see it much better. So let me resolve the 50 Newton. The 50 Newton will be resolved like this. And then the 70 Newton, I will resolve it. Okay, let me use a different color for here. Of course, you need to represent their correct directions. You know what I did? That representation of correct direction is important. So I represent this 78 Newton too. Okay, let's go. What's the value of the 78? This one, the red one on the 78 Newton side. What will it be? 78 cosine, is it not? 78 sine alpha. Do you agree? What about the blue one on the 78th side? That's the horizontal component for the 78th. What will it be?
Oh, 78
Cos alpha. Okay, let's go to the 50 Newton, the components. The red one is what? The red one is what?
50 sine alpha.
Theta. The angle there is theta, right? While the blue one is what?
50 cos theta.
50 cos theta. All right. So we've resolved the ones that need to be resolved. Let's get all the vertical. For it to be in equilibrium, the vertical forces must balance, isn't it? So what are the ones that are verticals? 78 sine alpha is upward, 50 sine theta is upward, right? So we can write 78 sine, where can I write this so that it will make sense? 78 sine alpha plus 50 sine theta must be equal to 112, am I right?
Yes.
You can call that equation 1. Sometimes you may need 2 equations to resolve this. That is for equilibrium of forces in the vertical plane. I could have written it. For equilibrium of forces in the vertical plane. For equilibrium in the vertical plane. In vertical plane. Alright, you have this. Now for equilibrium in the horizontal plane, what do you have? For equilibrium in horizontal plane, what do you have?
No.
That's the ones that are in the horizontal. Okay, tell me.
78 cos
Alpha must be equal to 50 cos theta, isn't it? Do you agree?
Yeah.
78 cos alpha is the one to the right, left. 50 cos theta is the one to the... Alright, so let me write it down. 78, you said 78 cos, where can I write this? Okay, I think I should just move them a bit. So for equilibrium, in horizontal plane, you don't have to write all this anyways. For equilibrium in the horizontal plane, you said 78 cos alpha is equal to 50 cos theta. Do we all agree? This one to the left, 78 cos alpha is equal to this one to the right, 50 cos theta. I think it is easier to solve this equation too. Cos alpha over cos theta will give you, no, they are different angles.
You've given us,
They are different. They gave, oh, they did. Sometimes if those things are not given, you can actually do equation 1 over equation 2 to get something that will cancel out. You will see questions like that anyways in the course of your work. Sometimes you may do equation 1 over equation 2 and you find sine theta, for instance, over cos theta. What is sine theta over cos theta? Trigonometry ratio, trigonometry identities. It doesn't apply in this case, but I just want you to recall that there are times you may need to, it's just like some of the tricks of solving simultaneous equation. Equation 2 divided by equation 1, or equation 2 minus equation 1, whatever you want to do. Recall that you may need to eliminate certain things. For instance, you may apply that principle and you end up getting sine theta over cos theta. What's sine theta over cos theta? Tan theta, and some things will be eliminated and then you continue. Not in this case anyway, because the angles are given. Alright, what is said? Oh, they gave us tan. Oh, you see, I think it is necessary. What I'm saying may still be necessary. Yeah. What I'm saying may still be necessary in this question. Or you don't think we need it? Okay, we have, they gave us in tan, so you can find them in cos. That is if you want to use Pythagoras theorem. Okay, what do you want to do? Let me ask you.
I thought you just do tan inverse of diffraction to get your value for E.
It is not always very neat. If you do that, there will be a lot of approximations that will drift your answer very far. I know you, when you do that, you get something point something. Try, for instance, tan inverse of 12 over 5. What's tan inverse of 12 over 5 for alpha?
67.3.
You know, you're getting point now. By the time you start applying that in subsequent work, your final answer will now be drifting away from. It's not that you won't get an answer close to what is in the math scheme, but it's just advisable to leave it. Do you understand what I'm saying? It's advisable to leave it in these fractions as given. Instead, I will ask you to get cos alpha. If tan alpha is 12 over 5, what is cos alpha? You may want to do that, even though it's too much work. Pardon?
You can use sec squared minus tan squared.
Oh, okay. Or use a trigonometry. You use trigonometry ratio. Let me put up a diagram to show you what I mean. If this is alpha, are you seeing what I've drawn there? Tan means what over what?
Sine over 4.
No, tan.
Oh, you know sine over
No, I mean tan itself. The trigonometry ratio tan means what?
4.
Opposite over what?
Adjacent.
So this place is 12. This place is 5, isn't it?
Yes.
Make sure you are seeing what I've drawn. This place is 12. This place is what?
5.
So what do you think the hypotenuse should be?
Uh,
Let's call it x. X is equal to square root of 5 squared plus 12 squared. It's better to get it like that, please.
It's still decimal. It's 24.51 or 5.
You can't give it in short form.
Yeah, that's just root 601.
Root 601, leave it as root 601. Root 601, right? Root 601, just like that.
Yes.
Root 601. Okay. All right. The same thing for the cos.
Wait, never mind. I made a mistake.
You made a mistake, okay.
It's
13,
13.
okay, you made a mistake. Because usually when they give this kind of question, they give it in a way that you can easily resolve it. X is 13, isn't it?
Yes.
So what is cos alpha? That means cos alpha will be what? Please, are you following? Please, make sure you're following. Are you following? No, don't use your calculator. That's why I want you to not to use your calculator so that your answer will not drift away. Use Pythagoras theorem to get the other component, the other side of the triangle. They said we are giving tan alpha 12 over 15, and you know tan is opposite over adjacent, so 12 over 5. So 12 is the opposite, 5 is adjacent. With that, using Pythagoras theorem, we can get x, the hypotenuse. So we've gotten x to be 13. So what's now cos alpha? 13 over 5. So you simply use that, 13 over 5. Please don't use the one that is in point something or your answer will drift away. Do the same thing for, did you understand this? Do the same thing for cos, the one for tan theta. Can we draw the one and get for tan theta? By the way, what's sine? Let's get sine alpha. Sine alpha is what?
Sine alpha.
Sine is opposite over hypotenuse now, isn't it?
Yeah.
Which is what over what?
12 over 13.
12 over 13. Are you sure everybody is following? So do the same thing for theta.
Because theta is
Let me just draw the diagram for theta.
5 over 3.
Tan theta is 4 over 3. Tan theta is 4 over 3. So 4 is here, 3 is here. Using your trigonometry, your Pythagoras triple, this must be 5. Good. Y must be 5. Here must be 5. Right? Without even wasting time. So if that is the case, what is sin theta?
5 over.
Sin theta is 4 over 5. And cos theta is what?
5 over 3.
5 over 3 over 5.
Sorry, 3 over 5.
Please, are we all following? Please use it. This is how we should be. This is how to do it.
Alpha is 5 over 13.
Cos alpha.
Yes.
Oh, 5 over 13. We wrote 13 over 5 instead. 5 over 13, sorry. Because alpha is opposite, adjacent over hypotenuse, 5 over 13. Alright, so that's what you do, and then you solve the rest, okay? Can you now use that and substitute into these equations? You can now get whatever you're looking for. Substitute them into these equations, You'll be able to get what you're looking for. Or into the equation for the top one. For instance, if you substitute it into this one equation, you will see that what is on the left is equal to what is on the right. So it's proven. Did you get that? Once what is on the left is equal to what is on the right, it's proven. For equation 2. Also, for equation 1, if what is on the left is equal to what is on the right, it is proven. Are we all here? Substitute these values into that you see.
For the first one is correct.
So we can see some other examples, like this one says 4 coplanar forces, F Newton, 5 Newton, 25 Newton, 15 Newton are acting at point P in the direction shown in the diagram. Given that the forces are in equilibrium, find the values of F and A. We have to find the values of F and alpha. So this is where we resolved the components. Of course, the 25 Newton does not require any resolution. Also, the 5 Newton does not require any resolution because the 5 Newton is already on the horizontal plane, so it doesn't require resolution. The 25 Newton is already perpendicular to the horizontal plane, so it doesn't require any resolution because the horizontal plane is a plane of reference. But the force F has been resolved. We have F sine alpha for the vertical component and F cos alpha for the horizontal component in their proper directions based on what we discussed earlier. Also, the 15 Newton force, this 15 Newton force was also resolved. We have this in the horizontal component, which we got 15 cos 20 or 14.10 Newton for the horizontal component, and 5.13, which is from 15 sine 20 for the vertical component. So all the forces that need to be resolved have been resolved into their components. Now, if the system is in equilibrium, as we are shown, or we are told in the question, then for equilibrium of vertical forces, the total forces upwards, which is only F sine 20 is the only force upward, must be equal to the total forces downward, which is this and this. This is 5.13, while this one is 25. And the only force upward is F sine 20. So, the only force upward is F sine alpha. F sine alpha is the only force upward. So for equilibrium of vertical forces, F sine alpha must be equal to F sine 15 sine 20 plus 25, or 5.13 plus 25. That's what we solved here, and this is where it is simplified. We can call that equation 1. So F sine alpha is 30.13, equation 1. Also, for equilibrium of horizontal forces, we have these all acting to the right. This one is F cos alpha and 5 Newton acting to the right. The only force acting to the left is the 14.10, which is 15 cos 20. So also for equilibrium of horizontal forces, we have this. We have F cos alpha plus 5, which are acting to the right, is equal to 14.10, which is the only force acting to the left. And this simplifies to F cos alpha equal to 14.10 minus 5, or F cos alpha equal to 9.10. So we can call that equation 2. We're able to obtain equation 1 by solving for equilibrium of vertical forces. This is equation 1. This is equation 1. And then we also obtain equation 2 by solving for equilibrium of horizontal forces. This is equation 2. So we have the two equations. The two equations have two unknowns, F and alpha. F and alpha. So our work here is to solve for F and alpha. And I mentioned earlier that this is simultaneous equation. We will just find a way of eliminating one variable and then find the other one. Eventually we substitute to get the other one. One way to do that is to divide. In this particular case, we can divide one equation by the other equation so that we obtain one of the popular equations in trigonometry identities, like sine alpha over cos alpha, which gives tan alpha, or sine theta over cos theta gives tan theta. So that's what we did here. This one is F sine alpha equal to 30.13. That's equation 1. Equation 2 is F cos alpha equal to 9.10. So what we did was to divide equation 1 by equation 2. And when we did that, we obtained this. Equation 1 divided by equation 2 will give us F sine alpha over F cos alpha equal to 30.13 over 9.10. And F sine alpha over F cos alpha, F will cancel out. We'll be left with only sine alpha over cos alpha. And sine alpha over cos alpha is tan alpha. So tan alpha is 3.13, which is 30.13 divided by 9.10. So we can easily get alpha by finding tan inverse of 3.13. That gives us 7.13. So we found alpha. We can just substitute into any of these equations. Maybe equation 2 or even equation 1. We have the value of alpha now, 73.2. That we can substitute into any of these equations. Equation 2, F cos alpha equal to 9.10. Or even equation 1. Equation 1, F sine alpha equal to 30.13 and get F. So we have our two unknown values, F and alpha. That's that. We can look at some other practice questions that we can attempt, like this one says, that's the one we just did now. Let's see this. I can zoom in. This one says coplanar forces of magnitude 34 Newton, 30 Newton, etc. act, given that sine alpha is this, sine theta is this, find the magnitude and direction of the resultant force of the three forces. So this is given. We should find the resultant force and find the direction. Remember, the resultant force and the direction, which is the angle that the resultant force makes with the horizontal axis. Makes with the horizontal axis. That's the direction. So we need first of all find the resultant force. Like we did in this example, the previous example we worked on. This is the first thing we did, where we found the resultant force. We got 20.69 as the resultant force, and then we also found the direction by using tan inverse of this over this. That's tan inverse of 20.26 over 18.91. Vertical, tan inverse of force on vertical over the force of horizontal. All right, that's what we expected to do here. For the other examples, we can apply a similar principle. Let's see this one. This is related. Let's see how we can go about this. This one says we are required to find the magnitude and direction of the resultant force of the three. I think that's what we just talked about now. We have this one too. I think this is related to the example I explained earlier. They are similar, so we can also do this. And then this one, let me zoom it in properly. Okay, this is the question. It says a particle of mass 0.2 kilogram is held in equilibrium by two light inaccessible strings PQ and QR. If P is a fixed point on the vertical wall and R is a fixed point on the horizontal wall, the angles which the strings PQ and QR make with the horizontal are 60 degree and 30 degree respectively. So find the tensions in the two strings. As a simple hint, the tensions are on these two strings, string QP or PQ and string QR. Now, the same thing we did in the previous one by resolving forces that are not on the plane of reference or perpendicular to it. So the tension is this T1 and T2. That's what we're expected to find. For T1, it can be resolved into horizontal and vertical component. For T2, it can be resolved into horizontal and vertical component. This 2 Newton is already on the vertical plane, so it doesn't need resolution. By the way, this 2 Newton is obtained from the mass, which is 0.2 kilograms. All we need to do is to multiply it by 10, that's G. You know, W is equal to mg. And in mechanics, we use 10 for G. You know, sometimes it might be required to use 9.81. W is equal to mg, where G is equal to 10, or approximately, or G is equal to 10 Newton per kilograms. The more precise value is 9.81 Newton per kilogram, but for the sake of this course, we'll be using 10 for G. Weight is equal to mass times G. You know, G will be using the value of 10 Newton per kilograms. That's how we came about these 2 newtons we have here. 10 newtons per kilogram for the value of G. So for a mass of 0.2 kilograms, it means the weight is 2 Newton. That's multiply 0.2 by 10, because weight is equal to mg. So we have all this. All we need is to find, because it's in equilibrium. We are told that it's in equilibrium. So sum of forces in the same plane, like vectorial sum of forces in the same plane, must be equal to 0. In other words, total forces upwards, which is only this one, must be equal to total forces downward, which will be these two. We form an equation. Also, total forces to the left, which is only this one, must be equal to total forces to the right, which is only this one. We form an equation. We can solve the two equations, simultaneous equation, to get T1 and T2. All right, we have another question here. It's the same principle. All we need is to draw and resolve the forces, and we get what we are looking for. So that's it. It says a small smooth ring of mass 0.2 kg is threaded onto a light inaccessible string ARB. The two ends of the string are attached to points A and B on a sloping roof inclined at 45 degrees to the horizontal, and then all of these are mentioned. The string is 70, is inclined at 70, which is this angle shown here, and the system is also in equilibrium. Find the tension in the string. The string is this is the string. The tension in the string. As a simple hint, I need to show that this string, the tension is acting towards here, you know, just like we did in the other one. The tension is acting towards the fixed point. That's the tension we're looking for, T. We're required to find this T, which is the tension. And the weight, of course, we know the weight acts vertically downwards, which of course will be 2 Newton. So if all are drawn properly, we can actually get what we're looking for. So the weight is 2 Newton. We get that by multiplying 0.2 by 10, because weight is equal to mass times G, which is approximately 10. So as that